So, good morning everyone. It's final time to continue with the coding. So, in the last stream I started implementing L2 regularization, but didn't really come that far. But now I've done some more reading, and I think I can continue with it now. So, first I started modifying the layers, so they also took an additional argument for the activation function. As we can see here, it says it's missing an argument, regularization function, but that function should be optional. So we will fix this. Let's go to the dense layer. We can keep this here and look on the left side instead. Okay, let's see. We're gonna look for, oh, and there's no music. There we go. We can look for the dense layer. Here we have it. Okay. So this doesn't have to be set. So only if it's not none, then we're gonna set the regularization function. That should solve this error. Let's try it. What? All right, this has to be none. Now it should work. Yeah, mode structure is correct. Perfect. So let's write down these results. So after the training, after plotting the data, we're gonna add one more code block, and we're gonna test the model just one final time. Wait, that's should be. Where do we use test? Do we use a test at the end? Yeah. Test X, test Y. And we get 244. Let's add some markdown and document this. Let's just go with basic. No regularization. Dropout. Well, actually, I think dropout is a form of regularization. Let me check that. Yeah, it's a type of regularization. So just keep this 2 decimals, should be fine. And let's scroll up to the L2 function I started writing the other day. We're gonna fix this a bit. Since we're using all right. I was thinking, since we're using means a gradient descent, we have to divide the result of this regularization function, but maybe we shouldn't do that here, because that would lock this L2 function to gradient descent. meaning it would not really suit stochastic gradient descent. So I'll leave this one because this I just swapped a lambda and weights. That's it. And maybe in the layer where we set the, maybe we shouldn't really set the function here. Yeah, we should. We must define set the function here, because we might have L1 in one layer and L2 in the second layer. So we're gonna keep this. And okay, so if you go to the test function of the model, so what we want to do here is that we want to add the result of the regularization functions for each layer to this. I think. Wait. And sum them up, I think. Yeah. That is what we want to do. Let's see. Split that up. We just do the normal class function, and then regularization functions, I guess. So we're gonna have to go through all the layers, I think. Okay, so let's call it layer is self dot a layer. We can go from the head to tail. That should be fine. Let's see. Well, layer is not layer. What is not? It does suggest some code here. Is this correct though? Okay, so when we're looking at a layer, if it is a layer, dense layer, we don't, that's kind of redundant. Just if it is a dense layer. So if we do have the regularization function, that's great. We add the regularization function 0, 0, 1. So this is our lambda, and he'll get the weights. Wait, do I have a function that called get weights? Have I prepared for this without knowing? Input layer. Oh yeah, you're trying to spam in chat. Get weights. Sorry, get weights. Layer set name for. Yeah, we do have get weights function here. Cool. This, however, the lambda. Where to find that? Is that for each layer? Should the lambda be unique for each layer? quick research. Okay, so it should be same for all. But maybe it doesn't have to be. Okay, so we want to perform the test. Maybe we should set the regularization lambda for the model. Maybe. I didn't see how TensorFlow did it. Okay. We have L2. Regularization. So they just assign the regularization type L2 to this dense layer. But where do they usually set the lambda value? L2. Okay, so it is for each layer. Then they do it. Okay. Then I suggest we add support for that too. Let's look for dense layer set regularization function. So we're gonna have self.regularization lambda. It's none. Take one more parameter. I know we might not be able to see this right now. Oh, welcome back. Nice to have you back in chat. Are you having first? Yeah, you're first, except for the spammer, the bot. Lambda, yes, that's correct. So you're gonna store that. You need to make check. So if we can have the default value there. So, okay, so now we also have a regularization function, regularization lambda. Spammers don't count. That is true. Spammers do not count. First from chat. Hello. Is there a live programming community like here on Twitch? I have no idea, to be honest. I just click on stream on YouTube as well for some reason. But I think most of the community is probably on Twitch. YouTube is mainly recorded videos, so. And welcome to the stream, by the way. Okay. So reset that. Let's go back to. Oh, before we do anything else, let's rerun everything. See if we have any error somewhere. Everything seems to be not working. Right, because of this. I'm rewriting the test function. Got one. Interesting. Oh, it's in. Oh crap! Oh crap! There we go. That's better. And so regularization function should only get one argument. Wait. No. There we go. I think that is fine. Run everything. Still working. Haven't broken it yet, so that's great. So we've added the regularization functions to the normal test here. So basically we just add the we first take the cost function and then add the penalty of the regularization functions. Perfect. So that's also still working. Just for fun, let's add a regularization function to this model. L2. We don't need to add the lambda because the default is 0.01. Now when I run this, the loss should be bigger. Like, pretty huge, but no. Type has no attribute L2. Oh. That's better. Okay. Does this good? Seems to be running. Maybe I can make a small test here. So we're gonna run the test with and without the regularization functions. So let's just get an additional argument here. It's true, false. Let's just call that one TMP. If TMP, well, if it's true, we should get two different values, and we do. Even though they're tiny, they will matter later on. So let's reset this. Should be working again. Yep. Would be nice for some early stopping here. I will add it soon. Okay, we added the cost function for the normal test. No, the regularization function for the normal test. Now I'm also going to add it for the backpropagation. So let's go to our layer, dense layer, backward propagation, and this update gradients with regularization. Yes, and it's probably gonna be able to complete the code for us here. Yeah, so if we do have the regularization, so if it's not none, we're gonna increase it for the weights, because we don't do this for the bias, only for the weights, because we want to keep the weights small. The biases has to be large, I guess, probably. So we just pass in the regularization function. This is almost correct. Almost. So let's see. This should be divided by the amount of entries. I think. Double check that. I've had like quite long conversations this morning with ChatGPT while doing a lot of Googling on this. So I'm kind of cheating, but hey, it's giving fruit. Or what do you say? It bears fruit? I don't know. Okay, so we do that. Oh, right. That is true. So actually here we're gonna use the derivative of the regularization function. And what will the derivative be? Right, okay. So it should be basically we just return the weights multiplied by lambda. Yeah, that's good check. But it says 2 times lambda times weights. Why? Let's see. That is true. It should be 2 times. So. This, by the way, are the loss function or cost function, whatever you want to call it. This is where we use mean square error, and then we just add the regularization term, which is L2 here. So this is correct. So we're gonna have to go to layers, self.regularization function, derivative. I see that I'm breaking the pattern here. Maybe that's fine. I could change this one though. To activation function derivative. Yeah, that should be fine. There we go. So we'll set this one. just gonna set the derivative like that. Sweet. And we're going to do the derivative. Give it the lambda. And the weights, this can be written shorter. I mean, we could just create a basic calling function inside the layer. So we move this. This will be removed basically, but we'll keep it like this for now. I think it's fine. And we also want to divide this by the number of entries. Amount of entries. Since we're doing Gaussian. Oh, Gaussian descent? No. Oh god, what is it called? All the words. Let me Google this. Gaussian descent? No. Gaussian process. What is it called? Gradient descent. Oh my god. Why Gaussian? Why? I don't know. I don't know why I'm thinking about Gaussian all the time. I better remember what it was. Gaussian distribution. What's that? Oh, right. Normal distribution. Damn. So I keep track of all the math. So we do have the derivative function now. We add it to the weights derivative. I think this might work. Let's reset the model grid first. Remove the regularization function. I'm gonna do this just to make sure everything's still running smoothly. Let's start at the top. I don't see anything weird. Yeah, seems to be working still. Very good. Now let's activate it for just one layer. Okay. I have to solve this somehow. But I wonder, should the regularization function be included in the testing? Right, it's not during the testing. So during training, regularization helps prevent overfitting by discouraging the model from learning overly complex or large weight values. Yeah. During testing, you're assessing how well the model generalizes to new unseen data. Why excluding regularization testing? When evaluating the model on the test set, you want to measure the true prediction power of the model as it stands out training. Okay. Okay. So I'm able to test with and without it. So just like I did earlier, I did modify the test function. Let's call this include regularization, set to false. And if that, let's highlight this. And so during the training, so here I'm gonna call the test. I think we want to print it out. Training, testing, though. Okay, let's keep it there. How about this then? Okay. $335, $364. All the results are worse. We'll test it. Let's improve the test function a bit. Print it out. Let's not print that out there. That's not a good idea. That's a bad idea. Okay, so test it. Set to false. If that one's true, would you add that? I think this is still working as it should. Let's add more of these. What? I had a... Oh. Crap, we can't have regularization on the output layer, can we? That should be fine, but here we have a problem. Let's go here. Bit about the matrices. Rows, columns. It's just 2 rows. Maybe we could skip support for regularization on the last layer. That's kind of stupid to do. So instead, we can fix the shape of it. print the shape. This dv shape, and also we don't need the division there for the shape. Something like that. Yeah, we have the shapes here, obviously. And we want this shape to be that one. So basically, if it is if that one's 1, then we should flatten it. So if regularization gradient dot size is 1, doesn't work. That one's 1. Then let's just update it. Squeeze or flatten. I think both will work. There we go. Fixed. Yeah. I gotta make a quick test here with the squeeze and flatten, just to remember how it all worked. Let's create a temporary numpy array. Holds 1, 2, 3. Then we're gonna print out 11. Oops. I'm gonna print out the squeeze. Okay, they work the same way there, but what's the difference? NumPy flatten squeeze. Ravel. Wait, is Ravel too? Ravel, flatten, squeeze. Oh my god, there's 3 of them. Should flatten view of original array key points. Okay, okay. Wait, so okay. Okay, so flatten doesn't, it like creates a new array. That's fine. And squeeze. This targets the removal of single dimensions. Oh, okay, okay. They're very similar, just tiny bit different. Let's remove the regularization from the last. No, you know what? Let's keep the regularization from the last layer. Why not? So that one failed. That one also failed. It did not fail. I'm curious why this suddenly became worse. 241, 260, 1067, 244, 260. Let's run this one until we find something better. Nope, nope, nope. Seven. 247 so far. Wow, the results are not amazing. I feel like the regularization made it worse. $214. Okay, let's keep that one. I know it's kind of cheating and not very scientific, but yeah, I'm just having fun. Okay, now we have that. I suggest add early stopping, because if we run this like doing these, just stupid. So we run 50 epochs with the training speed of learning rate of 0.1 up here, then 0.01 up here, and then 0.01 here. But this one should be stopped somewhere here already. So by doing this, we should be able to get better results. And we do see that there's like a slight overfitting, I guess. Sorry about that. Okay, so early stopping. Let's see if we can implement that. So that should be in the fitting. Early stopping. Let's take as none first. It should be a number. Each epoch. So we're gonna implement early stopping. If it's not none, that's correct. If the length of this is greater than 1, sure. Wait. What is this one suggesting? So we take previous one minus that one. I want the early stopping to be like an integer at like, let's say we set to 3, then after 3 epochs, if it's still increasing, then stop. Once again, let's see how TensorFlow did it. Just like set the patience of it. Okay. The patience will just be the value of it. So we're gonna have to create a variable up here to keep track of how it changes. Early stopping. Status. I guess. Set that one to 0. If early stopping is not none. And if self dot val loss history size or length. So it's not empty. Wait. If it's equal to or greater than 2, then if no. If that one is greater or equal to. Well, that won't really be equal to. That's kind of redundant check. Like the odds are so small. Let's remove that. Okay. There we go. And then if it's equal to early stopping, early stopped after blah 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 epochs. Break. I think this is all we need. Let's rerun it, make sure it's still working. Yeah. And where do we set the... Alright, it's during the training. The fitting. Okay, so let's give it patience of 3. Ah, I did early stopping. And with a good result. Let's implement this, all of them. 982. So we have way less epochs now. But this error remains. It's like it gets stuck. 272. Whoa, 215. Larger. Oh, yeah, I see. So the history of early stopping should not be up here. It should be inside the function. Self just like that. Loop through the epochs. It's like check input. No, not really. You can just look like that. We understand what's going on here. It's just variable. Yeah, we could stuck a high value. Something is weird with this model. Definitely. Wait. Oh, something's weird with early stopping. Okay, let's see. The latest one is greater than. There we go. 209. New record. Yes. 217. 202. Okay. 213. Can we get below 200? 195. 71. Okay, I'm satisfied with that. Wow, that's way better. And not like I think the early stopping fixed the issue with it like getting stuck at high values. The yes. No, damn it, it still happened. I would like to fix that. This. Maybe we can. Let's try to figure out what is happening here. Model.head layer. Next layer. Get weights. Okay. Do we have a get bias? Layer for get bias, yeah we do. Let's print. I don't see anything that's too weird. Looks normal to me. Like sometimes the test of training validation data gets stuck. Like validation is way down here, where training is up there, validation is down there. With training. So test error and training error. So that should be validation. Should it? Test something we do in the end. bugs. It might be a learning rate issue, bad weight initialization, data issue, probably not data issue, network architecture. No. Gradient explosion optimization algorithm. Bash size too small. I think there's something wrong with the weight initialization. Welcome to the stream, by the way. I hope you're having a great day. I'm trying to figure out what is going on here. Sometimes when I train the model, the loss result of the training set like starts high and that doesn't go down. So I was thinking maybe there's something wrong with the weight initialization. Why did I do that? This layer. Activation function, add neurons. Here. So we use heat initialization. Non-linearity of activation functions such as real activation, blah. Weight distribution. Okay. I am curious who joined the chat. But I guess I will never know who it is. Okay, so. For real activation, okay. Okay, duration of Why we're finding the derivative of it? Well, it seems to be correct, at least what we got. So a random number times math square root 2 divided by number of inputs. That is correct. Let's form prediction. Sure. Input size is not correct. Was it all columns and select them? Wait, what? Okay. Let's go to the prediction. X sets. Predict. Yeah. All size is not correct. Okay. If it's not 2. Okay. This is correct. We're gonna go back up to predicts. We're gonna say here, we're gonna scroll here to not backward, but or maybe backward actually. So we got model, look for backward. No, look for fit instead. We said predict with x set. This had to be multiple. That worked. We gave us 0. Interesting. Sometimes it gets stuck. It's like from the beginning. It never changes. Oh, it does change, but barely. Maybe the learning rate is too high. Nope. Does it decrease? Increased? Oh, right. If you need to put it else, we need to be able to reset there, stopping if we suddenly have an improvement again. We jump so much up and down, like. What if we remove the maximum and minimum values of the gradient just to see what happens? We're gonna go to layer, dense layer, under backward. We're gonna remove the clipping. Wow, that's not what we wanted. What if we make this smaller? We still have the same issue with these jumps. So we have 2 problems to solve. Let's start with this one. So in the beginning, all the predictions are probably 0. Let's scroll up before we do the fitting. And model.predict and train X. Like all the data, just predict all of them. Yeah, we can see all of them are 0. So we can't do the backpropagation. We do know that the data is correct, so could potentially be the normalization of the data. That shouldn't be it either. It must be the initialization. Okay, let's do 5 predictions, and we're gonna print out the output of each layer. I just broke something. Yes. Now this should, or holy crap. This is what I'm looking for. I'm gonna rerun this until it crashes. Shouldn't take too long. Hopefully. There we go. Now we're gonna look for the prediction here. First one, second hidden layer, third hidden layer. Okay. Suddenly becomes 0. That's interesting. Let's add some more code here. There we had a crash. If all these are 0, then this graph should be all messed up. Yeah. These sound too strange though. Take those two. There's something there. Let's remove the ReLib from the output. Oops. Wait, do you need to have an activation function? That shouldn't be required. That makes no sense. Let's go to layer, activation function equals none. If activation function is not none. Beautiful. I think this might have been the issue. Wait, there's more errors. Okay. Well, if it's not none. Well, if it is none, then we will just type self.a equals self.z, else we will run it through the activation. And here we have more stuff. If self.activation function is none, then the A and the Z equals what is that one equal? It's just one. I can think a bit about math here. I think it might just be one. I think that's correct. All has an activation function. Wait, what did I just do? Tail layer. Activation function. Has a T. Has an attribute T. Okay. So we're assigned to 1. Let's create a numpy array. Or just list. Nope. Times the length of the tail layer. This makes sense. This but it's like no. Okay. Up the gradient with the regularization. Non-type. So that one is L2. What? Okay, so we do reach L2. Let's minimize that for now. Okay. Where was I? I was trying to figure out what's going on there. Okay, let's go back down to the error. Less than or equal to doesn't support. It's not supported between instances of non-type and int. Yeah, that's the integer and there's non-type apparently. But the why is the none? We have apparently set the L2, the regularization function. Let's print that for fun. We should have some stuff here. Some print from that just prints none. Okay. That means that we should not even have the regularization function. But we do. I think I might have misplaced a line of code. Go to layers. Set activation function. This one should be moved to set regularization function. Okay. Let's try this again. It's beautiful. Did we set new record? No, we did not. Let's remove some of the printing, because I'm afraid it's a bit too much printing right now. Slows down the whole process. Those are fine though. Yeah. These are fine. Yeah, let's see if we can break it again. Yes. It doesn't seem to break anymore. It doesn't get stuck. Perfect. Ah. Okay, let's remove this. So the problem was that I had really low activation on the output layer. Okay. Still seems to be a weird print somewhere. Print layer name. No, we're not interested in those. Not that one either. Master for training. Nope, 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 nope. That one. Okay. I am happy with this result. Okay, so it doesn't get stuck anymore. There was a activation function issue. I think this is the next challenge. Like, take these huge jumps up and down. Could it be the maybe it is the learning rate that is the issue, but that shouldn't affect it this way. Like, this should just become smaller if we decrease the learning rate. Like, it's kind of spiky. So what if we fix the early stopping so that it stops early, like it counts up for each like increase and then counts down when 2 improvements have occurred in a row. That's a potential solution. TLDR, make sure you lost magnitude. Make sure your loss magnitude is independent of your minute batch size. Huh. Gradient clipping. Okay. Well, we already have gradient clipping. That does help us, yes. Let's improve the early stopping a bit. See what we can do with that. Or should we do some research on it? I just want to know what it does exactly, like mathematically. What is early stopping? No. What is needed? Increasing locks. Increasing. Wait, so the validation set is getting worse. Increasing loss, decreasing accuracy. Yeah. Or poor scores on the score matrix. Apply. Source overfits. So we need to go back in the history. Okay. So that's gonna be quite the mess. Okay, so I kind of misunderstood early stopping-ish. What we need to do is that we need to store all the parameters. Oh no, not the parameters. Yeah, the parameters for each neuron. A few steps, and then we notice that we're not getting it any better. We're gonna go back. Oh, damn. So if we train it to continue off this point, or stopping essentially turns the set parameters that use this point. So if we want to stop and train at that point, so the fine parameter returns will enable monitoring low variance and patch optimization. So let's say it keeps getting better and better and better. Poof. And if it gets... Okay, it's gonna take like 3 steps. If it gets better, we save that step. But if it gets worse, we jump back. Let's see. This is so confusing. Okay. It gets better, better, better. Oh. Then worse. Better. Worse. Worse. Okay. So we first have these 3. That. Then we get additional one. And see, oh, this one's worse. So you need to keep this one. The one before got worse. 1, 2, 3. Like this one. Better. Wait, they would keep this one, I think. Like, take the one that has the best performance out of those, like, compare them. You can also, maybe as soon as it gets better, we're gonna, because this one can be worse, but this one can be like worse than that one too. So let's say we're up. Oops. I have a line there and there. They're like, oh, it's getting better and better and better and better. And here we become way worse. But then it becomes better and then worse. Now this is a point we want to keep. Not this one. Meaning we always need to keep track of a certain number. And if that one keep track of X sets, let's call them sets. If first is best, load that and stop. I think this is how it's supposed to work. Because then here, let's say we have these 3. Then no. What? 3 of, let's say we keep track of 3. If the best one, oh. Okay, and if first is not best, oh, best thing continue. Because this one, this green dot could as well take us up here. And that's from where we want to continue. Okay, let's see if we can implement this. So the early stopping I implemented here was shit, so it doesn't solve this. But this implementation should. And when that is added, we have solved all the big issues. Then we can just try adding dropout and see if we can improve this further somehow. I don't know, maybe refactor some of the code or move on to some other part of the project, maybe MNIST classification. So under fitting, we do have early stopping. Here perform that. Should we keep a copy of the previous version of the model? Just copy it whole. We could just save the... Wait. We're not gonna make copies of the layers, we just want to copy the values of them. And... can we... maybe... no, those are objects. We could potentially save all the parameters of the whole model, create a function for that, so we can like import and export a model and do it that way. That is doable. So which one of these are interesting? So if it gets worse, we need to get access to that one. Gets better. Do we jump to that? Should we jump to that one or not? I don't think so. We should just reset. Okay. So you just need to save one set. We could save the neurons, but then why don't you just save the whole layers? See if we can just export function, I guess. No, not export function, but export model. Define export self. I mean, not real. Let's just create export weights. No. We can just export the neurons or export parameters. Maybe that's the best. Layer equals self.head layer. So while we're still looking at the layer, if it's a dense layer, I'm not gonna print those, we're gonna save those. Okay, so I'll just call this parameters. Parameters. And we're gonna append to that. Let's create numpy array. And weights bias perfect. Beautiful. And we're gonna return the parameters. Okay, okay. Should work. Let's run this first. And let's try model export parameters. Nope, missing arm. Oh, wait, MP array. Hey. Perfecto. Then we need to also be able to import the weights. Okay, so, oh, sure. Layer equals, if it's a dense layer, I in range, params. That is correct. That is correct. I think this might work. It might work. Okay. So let's create a variable here. Self last best parameters. It's none, okay. And down here, if early stopping, and if self the last best result, we need to also keep the last best result. Last best loss, I guess. If last best loss, if it is none, then we can store that result, and self dot last best parameters self export parameters. Damn, I'm getting spammed today by these. Well, not spam, just two of the spammers. Well, best viewers on star star star. Yeah, whatever. There's one over here. We will if it's not none, if it is none, or if the last loss history is less than last best loss. Okay, so we update it here. And if it's worse, then we increase the early stopping status. But we don't need to define these inside the model. We can store them inside the function. Like so. Okay. Let's get back to this. Sorry about that. Some personal matters. So we were implementing this early stop, and see here if it is none, just set it to these things. Oh, right. Remove self. go. Self dot. So right, that's correct. We increase that. If L something starts is greater or equal to, we can just set one to equal to. Early stopping. Okay. And we import the parameters. This could be it. See errors somewhere. That result is bad. Wow. These results are horrible. Not good at all. Oh. There's an error. Wait, what? There is a problem with how it imports the parameters. Without doubt. Okay, so take the first layer. If it is for each, okay, so we loop the parameters. That's good. Well, for each of them, if the layer is a dense layer, then no. I see the problem here. Ah, sloppy. That is what it is. So, we have our list. Let's say that we have our set here, our list here, one for each dense layer. So first, look at the first parameter, this one, set of parameters. If it's a dense layer, then we're gonna implement it. Yeah. If it's, oh, then we just go to the next, but if it's not dense layer, we're still gonna go to the next parameter. That's wrong. That is wrong. If okay, I do not really like this logic that's written. It's kind of backwards. You can say that. We could, what could we do? could go through all the layers. Okay, our layer is not none. I'm gonna just read through the layers and parameters, param index 0. And if is instance layer, dense layer, I for each instance weights. Yes, this looks more correct. And it was. Yes! A new record. A new record. Wow, okay, so that's 140.72. Let's run that again. Okay, that's worse. 163, 171, 144. Ah, that's scrap. 171. Ah. Yes. Yes, yes, yes. It seems to be working. It seems to be. It is working. It's working. Finally. Okay, let's go up to the top of my document. We have initialized, added L2 regularization, early stopping. We could also implement dropout, just because we can. It's not of code. It's not that much code really. It's just confusing stuff. So let's go for dropout and see if we can reach an even lower result there. Well, better result. And look, like it does early stop all the time. Maybe we can actually even push this further. Maybe not. Ah, what I had was fine. Ah, I am so satisfied with this. Let's add the dropouts. Huh. So, dropouts. How do you do the dropout? Need to read up on the drop. I think dropout is just during training. Regularization technique, the most randomly ignoring or dropping out some layer outputs during training. Just do overfitting. So do we add dropout as layers or do we add 2 layers? Per layer is implemented per layer in various types of layers, like dense layers. Okay, so adding 2 layers. Okay, I think it's pretty easy to implement. So we're gonna go to just a dense layer. We have our backward, we have our here we have it. Yeah, I'm definitely gonna want to refactor some of this code later. Okay, so self.dropout. Dropout rate, sure. Let's take that as an argument here. It's done. Perfect. Should we? I'm thinking we could initialize this as 0. Like, why not? Let's make it shorter. No, let's keep it none. Let's keep it none. And so during back propagation, backward. So it is the output. They're gonna zero out sometimes. Calculate the gradient, input, clip. So it's during predictions, not backpropagation. Yeah. So we need to know if we are doing backpropagation. Training false. So forward. Forward. Training. Let's call this is training. So that's a bit more explanatory, self-explaining. It's self-explaining. So we're gonna go to the input layer also, and therefore we're just gonna have is training false as default. I'm kind of adding redundant checks here, but I will keep them just because we can. Then we are gonna go to the, where are we gonna go? We are gonna go to the forward pass. Here's the forward pass. It's training. Yes, self A, it's output. Dropout. So if is training and self propagation dropout rate is not none, then oh, interesting, it's giving us some math here. Let's analyze that. Okay, so we multiply our output with binomial matrix. What is a binomial matrix? Okay. Just a bunch of ones. And okay. What? What just happened? Need to play around with this bit. mp.ones. So it's gonna require a shape. So first we take its number of neurons. We do 2, okay? Okay. And we turn that into an array. Okay. And we subtract the dropout rate. Where's the second argument? Binomial int p takes at least 2 positional arguments. Okay, n and p. No idea what they are. Just give me an example. Number of trials, probability for each trial. Doesn't go in 10 times. Does it 1,000 times? How do we solve this? We have ones of neurons, the chance, let's say 8, 2. Okay. And we'll grab the first element of those. Okay, this looks about right. They're gonna multiply it by this. Why? What? Why would we? There's a result. We just need that part. That's really all we should know or need. Let's add the dropout rate. So during fitting, it predicts. So this one true. And we're gonna set the dropout rate here. Nope. 0.1, sure. Let's go with that. I don't know. I'm just placing numbers now, basically. Oh, I have a crash. Beautiful. Predict takes 2 positive arguments, was given 3. Yeah. Is training false? Blah blah blah. Blah blah blah. Oops. That's not completely right either. Yeah, I see the problem. I see the problem. Yeah, well, it was correct, but under the dropout rate, we have to increase the dimension of this. Squeeze. Why? Why does it want to do that? What? This should be no. Let's try this again in a separate code block. Okay, new code block. Number of neurons, let's say 8. Dropout rate 0.2. Squeeze that. Perfect, that's what we want, but he wants us to also do some weird shit there. But this will give us larger numbers. Why? Why? I don't think dropout should. 1, 2, 3, 4. During train, dropout random deactivates the chosen proportion of neurons and their connections within the layer. This is 100% removes them from the network. The deactivation is chosen at random for each training iterations. This randomness is crucial for preventing overfitting. To account for the deactivated neurons, the output of remaining active neurons are scaled up by a factor equal to the probability of keeping a neuron active. That is, if 50% drop, the remaining ones are multiplied by 2. Oh shit! Huh. Oh. Huh. Then this isn't correct either. Right? Because this only sums up to oh, you know, let's TMP print TMP print sum TMP. This should sum up to 8, I think. If 50% drop, the remaining ones should be 1.2. Yes. Wait. Yes. So that's wrong. That is wrong. We need to fix that. How do we fix that? We will. Let me double check this math. I guess this is correct. Crap. Scale output. It is. Yeah, we have some problems here. It's fine. We can figure them out. Here we have the problem. Neurons and cannot be broadcast together with shapes. Okay. These are. Where is the shape problem? I'm gonna copy this. Print. Oops. That's we're not going to use the squeeze there. Okay, okay. I think the dropout rate is a bit low. If self dot next layer. It's not. We're gonna have to compensate for this. So if it is none, we know we're gonna have to squeeze this. You spell it squeeze. Is it like that? E. So blah 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 blah. We have this issue here. Doesn't match the broadcast shape. 1.8. Oh. What do we use? Flatten? No, no. I know what we're gonna use. We're gonna select the first index. And we can just remove this, do like that. Should be fine. And suddenly we have dropout. Let's see if we can beat 140 by increasing these values a bit. Yeah. 190. Sarball. Huh. Oh, let's double check this just to be sure. We're gonna take this and print that. Yeah, seems to be working. $100, $200, 1090, 165. No real improvement with just dropouts. 234, 171. Crap. Well, I tried. Validation goes a bit lower. That's good. 158. done. So go to the top here, remove some dropout. Yes. I am very happy with this result. This feels great. Okay. What is next? What is next? We could try classification of MNIST now. Maybe I will save that for some other time. So I think this might be a good place to end this stream. So I thank you so much for watching.